Hey class, this is the sample exercise 19.3. You can follow along with this on page 817. So if you want to do that, feel free to do that. Why is this not working here? Okay, there we go. Sorry. So 817 is the page in the book if you want to follow along with this. So here's what I'm going to ask you to do for all the sample exercises here. I'm showing you how to do some of the problems. I want to make sure that you understand why the answer is the way it is. So let's take a second to take a look at a couple of these. So for the first one here, well, first of all, let me say this much. You guys remember from the notes, I hope, that you have final minus initial for the entropy of a system. Now, the delta S is important because we're not really sure where it starts or where it finishes as far as like measuring the absolute amount of S for the final and the absolute amount of S for the initial is difficult to do. But when we subtract the two states, then it makes things a lot easier for us because we don't have to worry about where we start or where we end. It's just kind of like the difference between the two of them. Now, here's what I'm going to say. Remember, for enthalpy, enthalpy was like when something's giving off a lot of heat, let me just do this. When heat leaves the system, and the box is the system, into the environment, then our delta H is negative. Okay, so our delta H is a negative delta H when heat leaves the system because the system has less heat, and because it's leaving, that's a negative delta H. Well, it's a similar thing here. When there's more randomness to the system, it's positive. Delta S is a positive, more randomness. And when there's less randomness, when it goes from a more random to less random situation, then it's a negative. So I just want to make sure it's like you're clear about what's actually happening with the delta S. For the first one, notice the difference between the reactant and the product is that here and here we have the same compound. We have on both sides, we have the same number of moles on both sides. We have 1 and 1. The difference is that the water goes from a liquid to a gas. And this is called evaporation. Evaporation is clearly a case where the molecules go from one state to a higher state of randomness because anything that goes from a solid to a liquid is an increase of randomness, and liquid to gas is an increase of randomness. And of course, a solid to a gas is an increase of randomness. So that means that what we have here is a positive delta S because we're increasing the randomness from the reactants to the products. So take a look at B though. B is a little bit different. Notice that here we have a solution of silver ions and chloride ions, and they combine back into my molecule of silver chloride, which means in a solid sense, which means that no longer are they moving around like a liquid. So this would be negative. This would be a negative delta S because we're going from in a solution to a solid. Okay? Notice that for the next one, there's a change in the number of particles. So the number of particles does make a difference. If we have less particles, that means we have less microstates. So we go from having 7 moles total between the iron and the oxygen to having just 2 moles of the product. Okay, 7 moles total to 2 is definitely a decrease in microstates. Notice that this gas for oxygen also goes to part of the solid, which means that we also have then a change of entropy that is less random. And then finally for D, now take a look at D. D's an interesting case because we have 1 mole here, 1 mole here, and we have 2 moles on the right-hand side. Well, notice that they're all gases here. So there's going to be probably some change of entropy as to which way it goes. Honestly, you really can't be sure because there's nothing that we've used in the previous problems or in the notes would tell you one way or the other. You could say, though, that the entropy for this is going to be pretty close to 0 because there's the delta S because the state of the reactants and the state of the products is not much different. according to the information that we have. So we don't know exactly which way the entropy is going to go, the delta S. All right, one more. Take a look at the next ones here. What I would like you to do is I would like you to pause this. I would like you to give your own answers and see if you got it right. Okay, so pause right here, answer this, and then see if you have the same reasoning that I do. Okay, and we're back. The first one's pretty simple, matches up almost precisely with A of the other group, which means going from a solid to a gas is an increase of delta S, or a positive. Okay. Notice I have two compounds. They combine to form one compound. I start off with 1 mole of each, which means when I combine for the product, I only have 1 mole for the products. So that actually is telling me, and I'm going from a solid and a gas to just a solid, means that there will be a decrease. Okay, both of those parts there, oops. Both of those reasons, it tells me there's going to be a decrease. Okay, so, and again, very clearly for C, I have the same situation, 2 gases. So 2 moles of gas going to 1 mole of a solid is definitely a decrease, and it should be a decrease. Less particles, less number of particles, and those particles are in a lower state, which means solid. So here we have 2 moles of this gas, 1 mole of this gas, and we only have 2 moles of the other gas. I would say that this is probably going to be another decrease because I only have 2 moles on the right-hand side where I have 3 moles on the left-hand side, which means that you probably have, there we go, which means you probably have less microstates, so that'd be another decrease. I hope you guys did well with this.